Day 3 content. So we're talking a lot about the halogenation reaction last time, and that's a substitution reaction. If you recall, the halogenation reaction, especially the bromination reaction, is useful because a hydrogen that, if abstracted, leaves behind an especially stable free radical can be selectively removed over hydrogens that might be at primary sites or secondary sites, because the free radical there would be a lot less stable kinetically. The pathway that involves this hydrogen abstraction would be happening much more often, so you can selectively install a halogen at a site which otherwise wouldn't be reactive because of the hydrogen position there. So that's a reaction we're going to see a little bit more of today. And moving forward, it's especially helpful if you want to convert an alkane into an alkyl halide. And we know alkyl halides can undergo a variety of reactions, elimination, substitution, and so that's a useful transformation sometimes to make. So the next section in chapter 11 we're going to discuss involves a reaction we saw last semester, but we never really got a chance to explain it because we hadn't talked about free radicals. So last semester we said if we add HBr to a pi bond, which was in chapter 8, where we're doing, or no, that was chapter 10, where we're doing addition reactions. The pi bond can pick up a proton. Electrons stay behind on the bromine. And we said that goes through a pathway that will connect the proton on one of these two carbons selectively, because when the pi electrons come out to make that new sigma bond, it's going to form at the Markovnikov predicted site, because the carbocation that's left behind is more stabilized through hyperconjugation and induction at the tertiary site than it would be at the primary site. So we could imagine, alternatively, the hydrogen could add here, but that would leave a primary carbocation, which is really prohibitively unstable, so it's not going to go through that pathway. Right? So we had regioselectivity, Markovnikov addition across a pi bond to install the hydrogen at the site where there are already more hydrogens attached, because the carbocation is more stable and that kinetically is favored to go through a lower energy pathway. And then the bromide that would be created in that step would attack here and end up at that site. And then we said if we want to do the opposite of that Markovnikov addition and do anti-Markovnikov addition, we just need peroxides. But we never went through the mechanism or explained why, which is what we're going to do now, because now that we've talked about free radicals, we can explain this reaction. So here's what happens. So that's the point of the peroxides in this reaction, is because the two oxygens have the same electronegativity. They track the electrons pretty fairly. And so if one electron goes with each, all we have to do is heat that up a little bit. That homolytic cleavage of that sigma bond will produce some free radicals. And obviously that requires some energy to break that sigma bond. So this is basically the stability of that sigma bond in kilocalories per mole. Once the oxygen radical forms, because it's a relatively small atom, and that gap in the second is in that second energy level, which is close to the nucleus, it's pretty unstable to try to pull electrons away from a spot that close to the nucleus. So that oxygen radical will react quickly with HBr. Right, so the reaction here, just to remind you, is an alkene, and we're adding HBr across the alkene, and we're using peroxides. And the point of the peroxides is to start a radical mechanism. So then that radical reacts with HBr. So instead of the HBr adding across the alkene, as we saw in the last example, it undergoes a hydrogen abstraction to make an alcohol, and that produces a bromine radical. And since the radical now is on a much larger atom, it's a situation where I have an empty spot in the fourth energy level instead of the second energy level. It's not nearly as unstable to pull electrons out of the fourth energy level because of all the shielding. They're not as strongly attracted to the nucleus. So this is significantly more stable on the product side than the reactant side. So this step is favored exothermic. It releases a little bit of energy compared to the energy that must have been absorbed to break that sigma bond and form the radicals to begin with. So in the next step of the mechanism, this bromine radical that exists will add across the pi bond. And so here is where the regiochemical outcome is controlled. We said with the addition of the peroxide, it should be anti-Markovnikov, and that means whatever position already had more hydrogens, that's not where the hydrogen is going to go. If another hydrogen came in here and the bromine came in here, that would be Markovnikov. Anti-Markovnikov is the opposite. So that means the bromine has to come into the carbon that already had more hydrogens, and there's going to be a hydrogen that ends up connecting to the other site. So the way that happens, and the reason it happens, is because of the stability of the free radical. Right? So the other option, I could imagine, if the bromine came in here and added with one electron and connected here, and the other electron came out there, that would produce a Markovnikov addition, but it won't go through that pathway because the secondary free radical doesn't have as much stabilization through hyperconjugation as the tertiary free radical. So we're not going to get that. We're not going to get this set of arrows that I drew. We're going to get the original set of arrows on the slide. So let me just get rid of those. So what these arrows are showing is the lower energy pathway kinetically favored because the free radical will end up on a carbon that stabilizes at best compared to the other option. That's what we mean by this right here. So the bromine will come in and make a sigma bond and shift the free radical to the carbon. So typically a carbon free radical is not as stable as a bromine free radical because having that empty spot in the second energy levels, more unstable. The electrons normally get pulled closer to the nucleus, so they want to fill the second energy level more than they want to fill the fourth energy level of a bromine. But in this case, we have to also consider the fact that we're making a sigma bond from a pi bond. So going from the less stable pi bond to the more stable sigma bond slightly more than accounts for the fact that we're going from a more stable bromine radical to a less stable carbon radical. So this step is pretty balanced on both sides, but it does slightly favor the products because the sigma bond is more stable than the pi bond, despite the carbon radical not being quite as stable as the bromine radical. So then the addition will be finished. Yes, Akua, the bromine radical is more stable than both oxygen radical or carbon due to the bromine radical only having a vacancy in the fourth energy level, which isn't as strongly attracted to the nucleus, so it's easier to pull electrons out of the fourth energy level and leave a vacancy there. So once that carbon radical forms, it's relatively unstable because it's a vacancy in the second energy level, which is pretty close to the nucleus, and it's going to attract electrons in there. That electron is going to join up with one of the electrons from the HBr reagent, and that will regenerate another bromine radical. So effectively, overall, this step specifically is product favored or exothermic because the bromine radical is more stable than the carbon radical. So I'm forming a sigma bond, breaking a sigma bond, which is not really making much of a difference, but going from the less stable carbon radical to the more stable bromine radical is what drives this step forward. So overall, what's happening is a conversion of a pi bond and a sigma bond into two sigma bonds, and them being more stable than the pi bonds is what drives this process forward. So despite the fact we have to put energy in to form the radicals, the subsequent steps release energy and make that relatively product-favored process. Sometimes the radicals will join together and form sigma bonds. Other possible termination steps could be a situation where maybe the carbon radical combines with a bromine radical. Just to double check that, there's already a bromine there, so I want to make sure I get that. So that could create a very small amount of this product, where I get two bromines there. All right, so just to point out, this is the radical that we're dealing with here, and there's plenty of bromine radicals in there, so those could combine. But we see, why wouldn't the oxygen radical combine with the carbon radical if it's more unstable than bromine? So that's also a possible termination step, so we should also consider that. Great point. So if there's a bromine here, there's also potentially some oxygen radicals from the homolytic cleavage of the peroxide, so that could also combine, and that would give another potential product. So that could definitely happen. However, great point. However, these products here are very, very minor. And why is that? Because radicals in solution are very low in concentration and they almost never meet up. Right? So just like the other radical mechanisms we're seeing, it's the propagation steps that produce the vast majority of the product. There's very little free radical, really of any kind, in solution at any given moment. The amounts of free radicals are very low. So the odds of two free radicals finding one another when they're very few in solution is just not very good. So whenever a radical is formed, the most likely thing for it to bump into is some other molecule, because there's lots of those all around. There are very few other radicals for it to combine with, and since it's relatively unstable, it doesn't take much energy for it to react with whatever it bumps into most of the time. So that's why when we draw the mechanism, other than initiation steps, it's the propagation steps that are the key part of the mechanism that produces the vast majority of the product. So any product that I would imagine, like this one or this one, that could only form through coupling or termination is going to be a very minor product. So we wouldn't expect to see much of either of those due to the fact that the radicals almost never meet. When a radical forms, it's much more likely for a bromine radical, once it forms, to react with a pi bond, because that is a reactant, and I've got a lot of that in solution. So there's much more likely collision to occur. Likewise, for the oxygen radical, it's much more likely to react with NHBr. You might see some of the oxygen radical reacting here. That could produce a significant minor product. If the oxygen radical reacted here to produce a carbon radical, then I might have an OR group here instead of a bromine on the end. But that should be a minor product, especially if a little excess HBr is used in the reaction. So those things can be experimented with and optimized. So we looked at the delta H values for each step. All right, so let's look at HBr versus HCl and HI. Because last semester, when we did addition across an alkene using HBr and peroxides, we never talked about HCl or HI. And there's a reason for that, and that's because they're not very often spontaneous. They're usually non-spontaneous, meaning they don't really produce much product. Right? So again, if we're talking about whether or not an equilibrium favors products or reactants, we want to focus on delta G. We know if the sign for delta G is negative, it's going to be product favored. If delta G ends up being positive, we know it's going to be reactant favored. So let's look at the propagation steps. Those are the steps that produce the vast majority of the product. So those are the key steps that determine whether or not the product's going to be favored or reactant's going to be favored. So if we look at the propagation steps, the first one was where the radical adds across the pi bond. And in this case, the reaction is not product favored when I use HI. All right, so let's break down these signs and make sure we understand them. So why is the entropy term positive here? Well, what's happening is I'm combining 2 moles of reactants together to form 1 mole product. So I know the entropy is going to go down, right? There's more variety in the motion and positioning. When the particles are independent, they can move around separately than when they're all stuck together in one thing. So the value for delta S is negative because the entropy is going down, and negative times a negative gives me a positive. So all 3 of these are positive. I can't really avoid that. Why does HI have a delta H value that's positive? Well, because the iodine radical versus the carbon radicals, an even bigger difference in stability. So we're still going from a pi bond to a sigma bond. And from that perspective, we would expect the products to be lower in energy and more stable, and that it should be exothermic and releasing energy as the energy goes down. But because iodine free radicals have a vacancy in the 5th energy level, the first 4 energy levels are full, so it's only the 5th energy level that's missing an electron, and taking an electron out of the 5th energy level doesn't require much energy because the 5th energy level isn't close to the nucleus. So that's really not even that unstable to have a free radical in the 5th energy level, especially versus the 2nd energy level on a carbon. So in this situation, when I have iodine instead of bromine or chlorine, the halogen free radical is so much more stable than the carbon free radical. It's actually favored on the reactant side, despite the fact that the pi bond isn't as stable as the sigma bond. So because the reactants are favored in entropy and in enthalpy, there's no way to shift that equilibrium toward the product side, no matter how I affect the temperature. So it's just not a practical situation to try to use HI. So let's, so that's what we're saying here. HI will never favor the products because neither the enthalpy nor the entropy term favor the products. They both combine together no matter what I do with the temperature to give me a positive value for delta G, which means the reaction is going to produce more reactants than products when it reaches equilibrium, which is not what I want if I want to try to make the products. So if HCl and HBr, though, are negative, I've got a situation where I've got a negative term, and I'm adding a positive term. So if one of these is larger than the other, it's going to determine the sign for delta G, which is going to determine whether the reaction favors the products or the reactants. So what do I need to do with the temperature to make these 2 situations actually favor the products? Very good. Who is ready with the answer? If I lower the temperature, this number will be smaller and smaller. And so the term will be smaller and smaller. And that will decrease the size. The lower the temperature gets, I'll decrease the size of this term. And the positive will be smaller than the negative. So when I add them, I'll end up with a negative value for delta G, which means it'll actually shift toward the product side in that step, which will help the rest of the process occur as well. So the temperature here has to be just right. If it's too low, then there won't be enough energy for the collisions to get over the transition states, and kinetically the process will be too slow. If it's too high, then this positive term will be too large, and it'll shift the equilibrium back to the reactant side. So you always have to look at both the kinetics and the thermodynamics. And what we're seeing here is we need a low temperature to favor the products thermodynamically, but it can't be too low or it'll take too long kinetically. So let's take a quick look at the second propagation step. The second propagation step is where the radical abstracts a hydrogen to produce a product and regenerates the halogen radical. So in this one, what we're seeing is it's favored with HBr and HI, But we're already ruling out HI because it didn't favor the products in the first step. What we see here with the HCl is it doesn't really favor the products enough. So first of all, let's take a look at the entropy part of it. So here the entropy is close to zero. Why is that? Well, I've got 2 moles of reactants and 2 moles of products. So when I have equal number of moles of reactants and products, they should have basically the same amount of variety in positioning and motion on both sides, so similar amounts of entropy. So when the reactants and products have the same number of moles of particles, they have basically the same entropy, so the entropy term is going to be 0. So the sign for delta G is just going to depend on the sign for delta H. And when I have chlorine, the chlorine doesn't stabilize the radical enough. There's no hyperconjugation or resonance to stabilize it. It's a larger atom than carbon, so it stabilizes it, okay, but it's not as good as the stabilization of the free radical here with the hyperconjugation of the groups there. So in the situation with chlorine, this second step is reactant favored. So it's hard to drive the process toward the products you want if the last step of the process doesn't favor the products. So here's a situation where we might actually not have exactly 0 because there might be small differences in entropy, but the entropy term is basically negligible. And so we're focused on the sign for delta H. So because we're getting a positive value here, it's not product favored because we have a positive value for delta H. And that has to do with the stability of the radical comparatively on both sides. It's not as stable over here with chlorine as it would be with bromine or iodine because the bromine and iodine are even larger and allow that instability to be even further away from the nucleus, so it's not as impactful. HBr is the one that's favored in both propagation steps. So in both propagation steps are favored because they're both negative. That's a reaction that should give me mostly product, and that's why we almost exclusively do this reaction with HBr in the presence of peroxides, and HCl and HI aren't really involved. It's possible, just to point out in this bullet point here, that the negative delta G term in the first step of the propagation for HCl might be larger than the positive delta H term in the second step. If that were true, then combining those 2 steps together, I might still get an overall negative delta G, but it's not going to be very negative. It's not going to be as product favored as the HBr reaction. So we might as well just go with HBr if the goal is to put a halogen there that can act as a leaving group, because they're both good leaving groups. But the HBr should be more product favored because its delta G value should be more negative. So that means now we know the mechanism. Might ask you to draw it out and explain it. And we know that it gives anti-Markovnikov products. But we also want to look at the stereochemistry, or the spatial positioning of these groups with respect to one another. So when you're doing an addition across a pi bond, this should be familiar to you from last semester. So what's happening here is this bond is going to break. The oxygen radical is going to abstract this hydrogen, leaving 1 electron behind on the Br. The Br is going to add across the pi bond and leave an electron on that carbon. That will give me this. And then that carbon is going to pick up a hydrogen from an HBr to regenerate a bromine radical and produce the product. So which step determines the stereochemistry at this center? It's going to be this step right here. Right? This is the step where the bromine forms that sigma bond. So this is the step that determines whether the bromine does so from the front or from behind the structure. And that's the key. The structure is flat. A pi bond involves an sp2 hybridized carbon that is flat. There's a p orbital coming out of the plane and pointing back that the bromine will start to overlap with. but there's nothing blocking the bromine from coming in from the front or from the back. And since it's flat to begin with, you have equal probability of the bromine coming in from both sides. So in terms of the stereochemical outcome here, what we would expect would be half of the molecules would have a solid wedge here, 50%, and the other half would have a dashed wedge here. And those two happen to be enantiomers. They're non-superimposable mirror images because this is a chiral center in both structures and they have the opposite configuration at that chiral center. So that makes a racemic mixture. So that's what we would expect for that reaction. At least one of my reactants has to be chiral for the reaction to be stereoselective, or in other words, for me to get more of one stereochemical outcome than the other. At least one of my reactants has to be chiral. This is not chiral, this is not chiral, this is not chiral. If I look at all my reactants, it's kind of like a shortcut. If I see all my reactants are achiral, if I'm producing a chiral center in my product, there's no way to get more of one of the stereoisomers than the other. All right, so that finishes off that section. And now we get to finally talk about polymers. Since we had a lab on this already, hopefully y'all are a little bit experienced in this area, so it should maybe come a little bit easier than before. So in chapter 9, we didn't really cover this, but the textbook covers some ionic polymerization. There's a variety of different ways you can make polymers. And so what we did in the first lab and what we're going to talk about now are just one way. There's so much related to polymer chemistry, you could take an entire course on it if you're interested in that at a higher level chemistry course at a university if you transfer. So free radicals, though, are a pretty common way to make polymers, and it is the way we looked at in lab 1, where we used a radical initiator to start the polymer chains where they would grow from there. The basic idea is we have a monomer and we connect that unit to the next monomer and so on, right? So the idea here is typically in an addition polymerization, a pi bond is broken and it's it's converted into a sigma bond. So this would be a sigma bond to the next polymer unit, the next unit of the chain. And when that pi bond is broken, another connection is made to the next unit of the chain. So by breaking the pi bond and replacing that with sigma bonds to the units on either side of that monomer unit, that's where you can add parentheses, and that's the polymer itself. And so typically in a polymerization, you're converting pi bonds to sigma bonds. Sigma bonds are more stable than pi bonds. That's in part what makes the reaction work, going from the less stable pi bond to the more stable sigma bonds. But somehow we have to facilitate the collisions that will allow these sigma bonds to form. One monomer unit to the next, that unit to the next, that unit to the next, and then the parentheses or brackets are meant to show the repeating structure. So the pi bond in the repeating structure is gone, and it's replaced with sigma bonds that connect to the next units of that structure. So that's a general idea. So here's a way to think of that mechanism. This is usually initiated with homolytic cleavage. We used AIBN, a lot of us in the lab, which if you recall looks like this. What's nice about that is this carbon-nitrogen bond here can break homolytically to introduce one electron in here and the other onto that carbon. And then if the same thing happens on the other side, these two nitrogens now are disconnected from the carbons and one electron from each sigma bond moves in there, so I make a triple bond. And that nitrogen gas then bubbles out of the reaction and prevents it from going back. And so what's also produced there are these carbon-free radicals. You would get 2 of them. So whether it's a carbon-free radical or a lot of polymer chains are started by heating up peroxide, so that will break homolytically, create an oxygen-free radical. Whatever radical is created is going to start adding across the pi bond. So what's the problem with this is that it creates a primary free radical, which is pretty unstable. So ethylene or ethene is not a very good monomer. It's difficult for me to get over the very high energy transition state where this primary free radical starts to form because there's very little hyperconjugation, there's no resonance to stabilize it. So if you want this reaction to happen readily, you'd want to try to form a free radical that's maybe stabilized through resonance or more hyperconjugation. So if I put more groups here, a couple more carbons, and I use this 2-methylpropene instead of ethene, that would be more reasonable. I could get that radical to form. But just to keep things simple, we're leaving those methyl groups off just so you can focus on what's happening in the mechanism clearly. So whatever monomer you start with, there might be R groups here, there could be a chlorine or an oxygen or nitrogen, whatever it is. The key aspect of it is that the initiator starts to add across that pi bond. And every time a monomer is connected, the radical ends up moving to the end of the chain. And then from there, it can react with another monomer, and another radical moves to the end of the chain. And that continues over and over and over again until the chain starts to grow longer and longer and longer. So what if we did have an R group here? Well, it would still be here. That R group would help to stabilize the radical. It would still be here, stabilizing the radical. It would be here, here, here. So it would be every monomer would have that R group. And whatever the last monomer to add was would still have the free radical. And then that could add to another monomer. Right, so this is a really nice technique because if I can control what monomer I start with. If I want to make a polymer that has chlorines here, I start with a monomer that has a chlorine. If I want a methyl group there, I start with a monomer that has a methyl. If I want the polymer we made in lab, I just start with a monomer that has that connected. Right, so there's a ton of variety. The properties of the polymer that's created depend in part on what that group is. So if I have a bigger bulky group here, or if I have a more flexible group there, or if I have a group that can form some large partial charges and attract to water, I can make a water-soluble polymer like we did. So there's a variety of different properties that can result for the polymer depending on what that group is. The properties of the polymer also depend a lot on how long the chain gets. So what we did in our lab was to try to control how much monomer there was compared to how much initiator there was. And if these were in a 1-to-1 ratio, each initiator would react with one monomer and that'd be it. The chain can't grow unless I have many of these monomers for every initiator. So we set it up so that every chain that was initiated would have, on average, 360 monomers to react with it. And so the chain could be potentially 360 monomer units long if every chain grew to the same length. So once the chains grow, then eventually they terminate. There's a couple of ways that chains can terminate. A chain can randomly collide with a site that didn't initiate a chain. So if this radical forms during initiation and then it doesn't bump into a monomer unit to start a chain, it might bump into a chain that's already started growing and couple together and end that chain. So some of the chains might end kind of early. So it's really difficult to get all the chains of the same length. There are techniques for that, but that's more advanced than we have time or the need to get into. Some other chain that's growing might bump into another chain that's growing. If their free radical ends bump into one another just to make a sigma bond, then I end up with a pretty long chain usually, especially if that happens later in the process once these chains have had a lot of time to add a whole bunch of monomers to them and they've already gotten pretty long. So I might end up with some really long chains in my mixture. And so typically I get a wide distribution of the lengths of the chains. Some on average, some will be very small, some will be very long. On average, as long as all my monomer gets incorporated into one chain or another, I should have this average length controlled by the monomer to initiator ratio. But each individual chain length is going to depend on when it terminates, how many monomers were added before it terminated. So we can optimize and control the chain lengths using the monomer to initiator ratio, which is what we have here. There are other ways that are more advanced, so we're not going to get into unless you're really interested in that. I can talk to you about it individually. As we said, this particular mechanism that we're describing involves a primary free radical, which is really unstable. So that's usually not something that's facile or that happens easily. So with other monomers, if you had a tertiary free radical, or especially if you had a resonance stabilized one, that would polymerize so readily, it might start happening in the bottle just when you're storing the bottle. So those monomers are kept in brown bottles and kept at cold temperatures to prevent those reactions from occurring. And if you're interested, you can look at the end of the textbook where it shows some specialized catalysts that help to control polymerization reactions and facilitate polymerization reactions even if they go through relatively unstable intermediates, which normally wouldn't work well at room temperature without a catalyst. So sometimes polymer branching can also occur. So if I've got this chain already formed and it's got a hydrogen, you know, there's hydrogens at every one of these carbons. If another chain that's already started growing bumps into a hydrogen that's somewhere along the chain of another chain, that hydrogen can be abstracted. Right? So if this chain picks that hydrogen up, it terminates itself, but since it already has one electron, it can only bring one from the hydrogen, and the other from the CH bond has to stay now here. And so now instead of the radical being at the end of the chain and growing from the end and making all my chains straight, I've formed a radical in the middle of a chain. And then monomer can start colliding there, and so the chain can start growing from the middle instead of from the end. And that creates branching within my polymer. Sometimes you want that because the branching prevents the polymer strands from attracting as effectively. And if all my strands are straight chains, then they can all kind of line up, forming nice strong intermolecular attractions, and that makes a more rigid structure. And that would be something like the cap on a plastic water bottle or a squeeze bottle. Right? The cap is quite rigid. It's hard to bend because the chains have less branching. And there are different catalysts that can control the amount of branching as well. So there's a ton of control that you can exercise over this. We don't have time to get into a lot of the details. But if I don't control that, and there's a lot of branching that occurs, well then if one of these chains has a branch, it's hard for the next chain to attract to it. You know, maybe the next chain has to bend around in some way, and so there won't be as effective intermolecular forces between the chains, so maybe they can slide past one another or a little bit, or stretch a little bit as they're moving around a little bit, because if the attractions aren't as strong, it creates a little bit more flexibility for the material. So you get more flexibility with more branching because the intermolecular forces don't hold the polymer chains in as rigid of an arrangement next to one another. All right, so let's look at some specific polymers. So one is polypropylene. So I've got propene here, or propylene. So propylene is the common name, propene is the IUPAC name. So basically, if I connect this, so if I want to imagine what the polymer is going to look like, if I have a monomer and I'm trying to predict what the polymer looks like, which is what I might ask you, what you want to do is get rid of the pi bond and then just connect the two carbons from one unit to the next unit. And now I have the polymer. Right, so that results from an addition across the pi bond. So if you have the polymer, though, if you're doing a polymer through free radical polymerization, there's always going to be a pi bond, and that pi bond is going to add to the neighboring unit. So there will be two carbons in each repeating unit. Those two carbons used to have the pi bond. And so there might be things attached here. To imagine what the monomer would have looked like, which would actually mean I have to go back to imagine what the monomer would have looked like to form that polymer, I just disconnect the polymer from its neighboring units and reform the pi bond. So the pi bond is in the monomer. The pi bond breaks and gets replaced with sigma bonds on either side to the next unit of the polymer, right? So I'd have another unit of the polymer here, and that unit would be connected to the next unit of the polymer, etc. So I don't need parentheses for every unit. I'm just showing you how each unit is comprised of all the same atoms in the monomer, not taking away or adding any atoms. All I'm doing is converting the pi bond into a sigma bond, and then converting the pi bond of that into a sigma bond. So the sigma bonds link the units together, and that's how the polymers form. So if I want to make styrofoam, I need polystyrene. So I start with styrene, I add an initiator, whatever my initiator is, it adds to the pi bond. One electron comes out here, and this is a phenyl ring, so it's an aromatic ring. So what that produces here's my pH. As this oxygen forms a sigma bond, one electron comes out here to form a free radical. So what's nice about styrofoam is it forms very readily. It forms a free radical at the end of the chain that's stabilized through resonance. And then the next unit adds in the same way, producing another free radical that's still at the end of the chain as the chain continues to grow. But then I get this aromatic ring on every unit, and that affects the properties, depending on how much branching there is and how long the chains are. I might get, and whether or not air is injected into it as it's forming. I might get something that's more like styrofoam, or I might get a harder material like a petri dish or different harder plastics. Polyvinyl chloride is very common, especially for piping. If I replace all the hydrogens with fluorines, I make Teflon. And so here, the electrons are so strongly attracted to the fluorine. And the whole surface has the same charge. It doesn't form very strong intermolecular attractions. Right? Ever wonder why your nonstick Teflon cookware is so easy to clean and oils don't really stick to it, water doesn't really stick to it? Well, nothing can really form very good intermolecular attractions to this because they're not very polarizable. The fluorine is a small atom. It holds its electrons tightly. It doesn't allow the electrons to shift around and create lots of temporary partial charges all around the chain to help attract anything to the surface of that material. All right, so for the first question of today's quiz, I gave you the polymer, and I wanted you to predict the monomer. Right, so based on what we just said, these brackets represent what's included in each monomer unit once it's incorporated in the chain. So here, this is meant to show the chain extending in both sides. So if it extends over here, just to point out, I'd have another unit. So that unit is identical to this unit. And so just to point out, the brackets are meant to cross over the lines or bonds that connect one unit to a next, right? So there's no atoms here. This whole line is just a single bond between this atom and this atom, right? That line bonds the carbon of one monomer unit to the carbon of another. So really this is just a long chain with these groups hanging off. Oops. And so there's, if you just see the chain, you can't tell where the units are. You'd have to, the brackets are helpful in pointing out where the individual units are. So if this is my individual unit, what did the monomer look like that would have made it incorporated into the chain looking like that? So to go backwards and determine what the monomer is, I want to get rid of the bonds that are connecting that monomer to the next unit. And then just draw the atoms that are left over. And then the only other thing I need to do is to recognize there would have been a pi bond here. So whatever two carbons are actually part of the backbone of that chain, those two carbons would have had a pi bond because the radicals would have had to add across that pi bond to create the links between that monomer unit and the neighboring units on either side. You could have drawn it like this, or you could have drawn the cis version of that. So we don't have any stereochemical information here that tells us whether the methyl group here started trans in a position where the two hydrogens are on opposite sides, or cis where the two hydrogens are on the same side. So either of those would have been an acceptable answer to that question. Any questions about any of that? All right, so the next section is really a lead into chapter 12. And what chapter 12 is all about is synthesis. And I know that synthesis is a very common area where students have trouble. And the main reason for that is because we just don't have enough time to do the practice that's necessary to get really good at synthesis. Syntheses are like puzzles. They're not straightforward. Now, if you get a lot of practice working through puzzles, you'll start to get better at them, like Sudoku, for example, or other types of puzzles. People, crossword puzzles, if you don't know a lot of words, you're not going to be as good at solving crossword puzzles, but you can get better at them by practicing them. Same thing with synthesis. We all obviously have a limited amount of time to do this, though, so we want to try to be as familiar as possible with the ways to put answers together for syntheses and all the reactions that we've learned so far last semester and this semester that can be used to convert a reactant into a desired product. So we're just kind of review some reactions we talked about last semester and this semester, so we kind of have those in our toolbox to help us solve synthesis problems, and then we're going to look at some examples. So the radical chlorination, we said, is not as useful as bromination, so mostly we're going to be working with bromination. And the reason that's useful synthetically is because it is selective. Why is it selective? Well, we said if there are hydrogens on primary carbons or secondary carbons or tertiary carbons, or maybe there's a hydrogen on a carbon where it's allylic or benzylic, that would be even more stabilizing. But what we said is, in this reaction mechanism, what's going to happen once the bromine molecule opens up by getting hit by lighter heat, it's going to form a bromine radical. And then that radical is going to abstract a hydrogen and leave behind an electron. During that step, a significant partial radical forms on the carbon. And if that forms on a primary carbon, it's much higher in energy during the collision. So it won't go through that pathway. if it forms on a secondary carbon, still significantly higher in energy than a tertiary carbon. So what we'd see instead, selectively, is almost every structure would go through this mechanism where the free radical forms on the tertiary carbon, because the extra hyperconjugation there can really help to stabilize that during the transition state much more than it would be stabilized to form on any other carbon. So as long as my initial structure has one site that can stabilize a free radical better than any other site, I can pretty much guarantee that almost every molecule will go through the reaction and install a bromine at that site. So you want to work through some practice problems that involve this free radical bromination reaction and get used to seeing where it's going to occur based on the selectivity and stability of the free radical that forms on the carbon during the mechanism. Let's skip this part over. When we're dealing with bromine, we don't really have to worry about that too much. We would just use one bromine for every one molecule. And once it reacts at that site, we don't really have to worry about it reacting at the other sites because they're going to be much slower than the reaction at this site, since this site goes through a much lower energy transition state where a partial free radical forms on the tertiary carbon versus the much higher energy transition state where the free radical will have to form at a less stable site. So we can also do chlorination, but the problem with chlorination is it's really difficult to avoid polysubstitution. Once chlorine reacts, since chlorine's not nearly as selective, the transition state where the chlorine would react at a secondary site or a primary or a tertiary would be basically very similar. And once a chlorine picks off one hydrogen, if there's another hydrogen on the same carbon, that's especially susceptible to being replaced because that would also go through a free radical. And this chlorine here would be able to shift an electron in there to stabilize that free radical through resonance. So the synthetic utility of the chlorine is limited. We can't really do chlorination. It's difficult to control and prevent multiple chlorines from being added. It's difficult to control which carbon the chlorine adds to. So in a scenario like this where all the carbons are equivalent, it doesn't really matter which one it adds to. We get the same product either way. But once it adds, we can't prevent another chlorine from coming on there and ending up with di or tri or multiple substitutions around the structure. But the bromination is nice. If we have a substrate or a molecule where one site is significantly more reactive than all the others, like we had over here, because there's one tertiary site and all the others were either primary or secondary, and none of them are stabilized by resonance, that's a situation where we can use this reaction in a controlled way to give us a desired product. So here's an example. So let's say I want to synthesize some structure. I want to synthesize a target molecule from an alkane. That's challenging because an alkane is just carbons and hydrogens. There's no leaving group. I can't do a substitution very easily. There's no alkene. I can't do an addition reaction. There's no leaving group to allow for elimination. All the reactions we talked about last semester required either a leaving group or an alkene or an alkyne. This doesn't have any of that. So this is really the only reaction we have. We can use Br2 with light or heat, or we could use NBS. We talked about NBS and how that works. It does a substitution just like Br2. In this case, either would work. That would remove this hydrogen. The hydrogen would join up with the bromine radical, leaving behind a carbon radical, and then that carbon radical would pick up a Br at that site. And it's happening here specifically because the tertiary site stabilized the free radical better than any of the other secondary or primary sites. So I can control that and produce that product in a relatively good yield. Once I have the bromine attached, now there's a variety of other reactions. It's a good leaving group, so it could leave and produce a carbocation. And then I could get some nucleophile, just call that X, to come in there and do a substitution reaction. So I can't do a substitution on the alkane, but I've got this one special reaction that will actually react with alkanes to put a bromine there, which can then undergo substitution with a variety of different nucleophiles. So I can create some structures that I want potentially this way. We also know, since it's a good leaving group, we could do an elimination reaction. If I select the right base, it might come in and grab this hydrogen here. If this one ends up anti-periplanar to the bromine, to do an elimination, I'd use a base, try to set up an E2 so it works in one step, push out the leaving group, and that'll give me the alkene there. If I use a much more bulky base, one that can't really get in there because maybe it's a little more sterically hindered, I can get the less hindered hydrogen, push electrons in there, so I could also produce the alkene in this position. So if you remember from OChem 1, the base we used to grab the more sterically hindered hydrogen was normally ethoxide or methoxide. The bulkier base that would make sure that we would go for the more available hydrogen, even though the double bond's not a substitute with carbon, so it's not as stable as this product, that would have been the terbutoxide. Right, that terp-butyl group's too bulky to come in anywhere other than the most sterically available or less crowded site, at least for the majority of the product that would form that way. All right, so let's look at some syntheses. So they make in the textbook this analogy between solving a synthesis like building a home. You know, if you want to build something, you have to know the pieces you're going to put together. You have to know the tools that are available. Otherwise, you know, you're never going to build it. So you have to get familiar with the tools, how they work. And so in that analogy, the tools are the reagents and reaction conditions. So that takes a lot of practice. Right? You're not going to be good at building a home or home improvement as well unless you practice. So what's the reaction here? Anyone remember what reaction conditions we need here from Chem 1? So Kua says Br2 and metal. So we don't need the metal. So probably what you're thinking of with the metal is if you want to add hydrogens across there. So H2 works with palladium or platinum or nickel typically. And the metal surface attracts the pi bond and the hydrogens get added across the pi bond. So that would give you an alkane. So if you want to convert an alkene into an alkane, hydrogen in a metal is your best bet. Here, though, we would want to specify that we would want to do this in the dark. And the typical solvent for that is carbon tetrachloride. And so probably want to practice up with some of this OChem 1 stuff and get some of the details solidified in your mind. Otherwise, these problems are going to be very challenging. This is only a one-step synthesis. So once you get into 2, 3, 4, 5-step syntheses, it's going to be very hard if you're not pretty familiar with most of the reactions. So why are we doing this in the dark? Well, we want to avoid it. If we use light, that would open up as a free radical. And the free radical might start reacting over here to produce a resonance stabilized carbon free radical. We don't want to do that. We want to keep these hydrogens on here. So if we specifically want the Br2 to add across the pi bond, that's why we do it in the dark, to avoid the formation of any free radicals. So if you recall the mechanism for that, the pi bond picks up a bromine, The bromine attacks it back, and this bromine is a leaving group. That's the one that forms the three-membered ring. Once that three-membered ring's formed, it can be attacked by a Br-. Which carbon here is the Br- going to attack? Well, if sterex was the main issue, it would attack at the more open site. But this is just a single atom. It's not very sterically bulky. And if you recall, we learned last semester, these three-membered rings with a positive, we saw bromine, chlorine. Sometimes we saw an oxygen in here that might have 3 bonds, a lone pair, so it would be a positive in a three-membered ring, or mercury in a three-membered ring. We said typically the bond to the positively charged atom will start to break from the side that pulls electrons away from the carbon that can stabilize a positive charge better. So since this one can start to break, start to pull electrons away to stabilize the positive and pull electrons away from a carbon that can also pretty effectively stabilize the positive due to hyperconjugation and induction, that will attract the bromine into that site. So that one should attack there and push these electrons out, and that should give me the product. So Br2 there is what we needed, specifically in the dark. So to some degree, solving these requires some memorization, but to a large extent, practice can make these reactions relevant in your mind, especially if you practice with the mechanisms. So memorizing the outcome isn't always necessary if you understand some of the fundamental principles that are at play and why the electrons move the way they do, as we just explained, right? So I use the mechanism here to help me rationalize why the product forms the way it does, so I don't necessarily have to memorize exact outcome of these specific conditions with that alkene. But if I know the outcome and I know the reactions and I have a fair amount memorized, that can also be helpful because then I know what these tools are capable of, and I can start to imagine what tools are necessary to convert some reactant into some product. All right, here's another one. So there's also, some degree of strategy involved. If you go through these steps, it's not going to necessarily give you the right answer, but it's at least going to help you think about things in the right way. One of the biggest mistakes that students make here is to skip step 1. If you just look at the two reactants and you try to imagine some reaction that's going to do it, it's going to be very difficult. In the process of analyzing the structures, one of the key things I highly recommend is drawing in the hydrogen atoms around the area where the reaction's occurring. Right, so if I can show that there's one hydrogen here, not two, because it only need one to make this carbon's complete noble gas configuration, and there's still a hydrogen here because the carbon needs to have 4 bonds to be neutral. That means I don't have to add a hydrogen to that site. But if I look at the other carbon, which here is shown to have 1, 2, 3, 4 bonds, and here only 1, 2, 3, I know there's a hydrogen here. So clearly I have to add a bromine to this carbon, which everyone probably saw initially right off the bat, but you may not have seen initially that a hydrogen has to be added to this carbon. And so by analyzing the structures before and after, I can clearly see I need to break this pi bond, and I can clearly see I need to add a hydrogen here and a bromine here. So if I need to add a hydrogen and bromine, I'm thinking about maybe adding HBr. But then I have to decide, is it a Markovnikov addition? Is it an anti-Markovnikov addition? Do I need peroxides or not? And probably the best way to answer that is to think about the mechanism. So if I add HBr without peroxides, what's going to happen is the pi bond is going to pick up the hydrogen, because this is a really strong acid. The bromine is going to take those electrons and stabilize them. And that's going to produce a product, temporarily, an intermediate. When the pi electrons pick up that proton, it could add the proton here as we want, but that would produce a secondary carbocation. If it picks up the proton and adds it to the other carbon, pulling the electrons away to form another hydrogen connection at this carbon. As the electrons get pulled away, it would leave behind a carbocation here. So if these two pathways are possible, and one goes through a much more stable intermediate stabilized through hyperconjugation and induction more than the other one, this is not going to happen. So I can't just use HBr just because the hydrogen and the bromine are the atoms I'm trying to add across that pi bond and expect to get this product. Because using HBr, as the bromine takes those electrons, it would be a good nucleophile, it would come in there. It's not going to give me the correct regiochemical outcome that I want, if that's what I want. And so that tells me, okay, I need peroxides. I need the peroxide specifically so that when I heat that up or use a little light to break that open, instead of reacting this way, the pi bond well, first, as we showed earlier today, the peroxide would pick up the hydrogen from the HBr. And that would produce a bromine radical. And the bromine radical would react across the pi bond. And that would leave a tertiary free radical, which would be more stable. Then that tertiary radical would pick up the hydrogen. So that actually does give me the correct regiochemical outcome. So that's why I would need peroxides in that reaction. And so the more you have a decent understanding of the mechanisms, the more it can help you decide what reagents to use beyond just memorizing what different sets of reagents will do. If you recall from last semester, we talked about how to shift a halide from one carbon to the next, and that was a two-step process. You eliminate the halide controlling where the pi bond goes, and then you add the halogen back across controlling the regiochemical outcome again. Right, so specifically to do that in this reaction, I want to remember the less bulky base would go for the hydrogen, and again, understanding the mechanism is really helpful here. It would go for the hydrogen that shifts electrons in, pushes out the bromine. That's more, produces an alkene that's more substituted with carbon groups because it's more stable than the other potential alkene. And since this is ethyl, the ethyl group's small enough to access that hydrogen, it can produce the more stable sigma bond or more stable pi bond on the products and as the electrons are moving, right? So also during the transition state, as these bonds are breaking and forming, that would produce a pi bond or start to produce a pi bond during the transition state that's more stable than if we were starting to produce a pi bond down here by picking off this hydrogen. But if I used a much more bulky base, the tributyl group is more bulky, it probably wouldn't be able to work its way in there very often, so it would be more likely to pick up the less sterically hindered hydrogen, pushing electrons in, making the pi bond at the other site. So knowing the factors that are involved, the principles of sterics, and the fact that more substituted pi bonds more stable than one that's got more hydrogens. If it's more substituted with carbons than hydrogens, more stable. Now helps me to determine which reagent to use to produce the product I want. So if I then specifically want to add a bromine here, I could use HBr. That would give me a Markovnikov addition, right? It would come out here and pick off the proton, adding the proton to this position, leaving a carbocation here, and then the bromine would attack there and add in the position if that's where I wanted it. If I want to add bromine to the anti-Markovnikov site, I need the peroxides, which we just showed the mechanism for on the last slide. So there's a lot of specific reactions we talked about. Here's another slide that shows some of the reactions from last semester. So maybe you have to start with an alcohol. If you have to start with an alcohol and you want to make an alkene or move the alcohol to another position or replace it with some other group, you probably would need to start by converting it into a leaving group. So if you remember last semester we talked about tosyl chloride and pyridine. That step converts the OH into an OTS. And what is an OTS? If you don't remember, the OTS looks like this. Sulfur there, and an aromatic ring with a methyl group on it. So what's nice about that is it's a great leaving group. If the oxygen were to leave as an OH, the negative wouldn't be well stabilized. But here if it leaves, the negative is stabilized through resonance with 3 oxygens. So that's great resonance stabilization for that negative. So this is a great leaving group. So by using these conditions, I convert the OH into a much better leaving group. Then this structure is basically the same as this structure, whether it's a bromide leaving group or a tosylate leaving group. It's a leaving group. It's a great leaving group. So I can use this less sterically hindered base here, just like we showed, to take off the hydrogen anti-paraplanar of the leaving group to make the pi bond that's more stable. Or I could use the more bulky base we talked about to grab the hydrogen. Oops. That would be anti-paraplanar to the leaving group to make the less stable but also less sterically hindered during the transition state to form that pi bond. If you recall, you can also add a hydrogen and an OH across a pi bond. You can do that in a Markovnikov fashion, or you can mix it up and do that in an anti-Markovnikov fashion, and that depends or determines what set of reagents to use. So this aqueous hydration involves the pi bond picking up the proton first, making that CH bond and leaving a carbocation that a water will attack and then be deprotonated to leave behind an OH in that position. Here I get anti-Markovnikov hydration. All right, so the second step here, we didn't talk about the mechanism, so that requires some memorization to know what reagents you need to put there. But in the BH3, what we said is for 2 reasons, the boron will add to, oh, sorry, there's no pi bond there. Let me get out here and get back in so we can draw that in. So here, the boron and hydrogen add across the pi bond at the same time. And since the BH2 is a little bit more sterically bulky than the hydrogen, it goes to the carbon that's a little less sterically hindered than the one the hydrogen goes to. And more importantly, because hydrogen is slightly more electronegative than bromine, it carries a slight negative, and the boron carries a slight positive. So the pi electrons will come out there and attract to that. And that connection will happen at the primary site because the electrons are pulled away from the site that can stabilize a positive better site, which is the secondary site. But at the same time, the hydrogen will bring those electrons in and start to bond there. So only a very minor partial positive will form there during the transition state. Once the boron and hydrogen are added, the second set of conditions replaces the boron with an OH. All right, so we know if we have an alkene, we can do Markovnikov, we can do anti-Markovnikov. If we have a halide leaving group, we can determine the regioselective outcome of the elimination of that to get back to the original product. We can get a different alkene if we pick off the more available hydrogen with a more bulky base. And so there's another reactions, examples of some of the reactions from last semester. Now, from this semester, we obviously know that we can replace a hydrogen with a bromine. We can do that selectively if there's one hydrogen on the structure that, if abstracted, leaves behind the most stable free radical compared to any other hydrogen on the structure. And so now that gives us the ability to go from an alkane to an alkene. We never really filled in that gap last semester, but it's a 2-step process. The first step would convert the alkane into an alkyl halide. Then the base, which would be negative, would pick off the anti-paraplanar proton and push out the leaving group to make the alkene. So this is just a general, so this, you can do it specifically with this molecule, but just more generally, this is a way to replace a hydrogen with a bromine, which is a leaving group, and then as long as there's a beta hydrogen, abstract that, or do a proton transfer on that to make an alkene. And so you also want to be familiar again with the reactions we talked about last semester, where you can convert an alkyne into an alkene into an alkyne, etc. All right, so let's look at some examples. What do I need to do here? So first thing I want to do is analyze the structures. Probably the first thing I want to do is to count the carbons to make sure there's no change in the number of carbons. So I've got 9 carbons on the first structure and 9 on the second structure. So I'm not changing the number of carbons. So the next thing I want to do is to draw in the hydrogens, as we said, in the area where the reaction is occurring. So on this carbon here, there was initially a hydrogen. On this carbon here, there's initially a hydrogen. So I've got to get rid of 2 hydrogens and replace them with OH groups. So there's no reaction that will do that in one step. And we also know if you have an alkane, the only reaction we've talked about is the one we talked about this semester. So we know that the Br2 or NBS and light is your best bet. There are 2 tertiary sites. So there's no way to control which of those is replaced with the bromine. So if I do this reaction, after the first step, I'm going to get 2 products. Some of the products will form when this hydrogen is replaced with the bromine, and the other product will be produced when the other tertiary hydrogen is replaced with the bromine, which would be this one. I don't really have to separate these 2 from one another though, because if I'm thinking about the synthesis, the next step should work on either of them. But maybe I don't know what the next step should be. So maybe I want to try to work backwards. There's one reaction we talked about last semester that will install OH groups on adjacent carbons. There's actually 2 reactions that'll do that. In this case, it doesn't matter which one I use because this is not a chiral center, and neither is this. So the stereochemistry that I need isn't important. It's not an important consideration. So if you recall that reaction, there are 2 different ways to do that, but they both come from an alkene. So I have to have a double bond here before adding the 2 OH groups. I can add the 2 OH groups by using osmium tetraoxide, or I could first make an epoxide using MCPBA. Oops, I got a space there. MCPBA, followed by H3O plus and water. If you don't remember those, you've got some reviewing to do. So those 2 options either of those would add OH groups across there. The osmium tetraoxide would add the 2 OH groups to the same side of the pi bond. This set of conditions ends up adding the 2 OH groups to the opposite sides. But since these are not chiral centers, it doesn't matter whether they add to the same side or the opposite side. I get the same product either way. So then the question becomes, how do I get from here to the alkene so that I can use these conditions to make the diol? And that's elimination. So either way, I want to pick off a hydrogen from a tertiary site to push electrons in and push out the leaving group to make the double bond. And since this is a tertiary site that these hydrogens are attached to, it's pretty bulky, I wouldn't want to use a bulky base. It wouldn't be able to come in there, which might instead grab maybe this hydrogen here and make the alkene in the wrong position. I want to use maybe an ethoxide, which would normally be used in ethanol. The ethoxide would be small enough to grab the hydrogen, even though it's a little crowded, and produce the alkene in the spot where it's most substituted with carbons, because that would be most stable. And then 3 would be one of those two. So that's the logic for working your way through that example. As we were saying, first thing you want to do is to check the carbon skeleton. Right, we learned a few reactions last semester that alter this carbon skeleton by adding carbons. Some reactions will increase the number of carbons. We actually learned only one that will do that. Last semester, we're going to learn a lot more this semester. And we also learned a reaction that will decrease the number of carbons. So let's review those. So here's the reaction for increasing the number of carbons in my carbon chain. That involves an alkyne that's been deprotonated. Right, so this has got 4 total carbons. 1, 2, 3, 4. So what base do we need to deprotonate? It's got to be strong enough. The base we talked about was NH2-. The negative on a nitrogen is less stable than the negative on a carbon, specifically if that negative on the carbon is in a compact sp orbital versus the negative on the nitrogen being in a more elongated sp3 orbital. So there's a lot of detail from last semester we're going through quickly. Doing this to try to jog your memories as well as point out the important areas where you might need to review. So once that base picks off that proton, electrons stay behind, I get a great nucleophile. This is also a good base. So if I have any kind of tertiary or secondary leaving group, it would be more likely to pick off a proton and do an elimination. That's not going to increase the length of my carbon skeleton or the number of carbons in my structure. So I don't want that. So if I'm going to use this as a nucleophile, I have to have my leaving group on a primary carbon. That's the only way to make it so it's not too crowded for the SN2 nucleophilic attack to occur. So this can come in from the back side and push out that leaving group, connecting, let's call this carbon 4 with carbon 5. So we're making this new sigma bond by having one carbon act as a nucleophile, attacking the other carbon. It's an electrophile because it has a leaving group attached and a nice partial positive to attract that negative in. So this allows me to extend my carbon chain, add more carbons, and control the structure. The reaction we talked about that cuts a molecule into pieces, decreasing the number of carbons, is the ozonolysis reaction. So if you recall, any alkene can be broken and the carbons that were connected are now separated. With ozonolysis, this one you kind of just have to memorize a little bit. The 2 carbons that had a double bond each end up double bonded to oxygen instead. What would be the result if that were a triple bond? And I used ozonolysis. Well, it would be similar in that it would break the carbons apart, but now the carbon only has 1 bond, so you would end up getting a carboxylic acid for this carbon. It's carbon 3. The other carbon of the alkyne, since it was at the end, will be fully oxidized into carbon dioxide. And that would bubble out. So that just decreases the carbons from 4 total to 3 total and converts the end carbon into a carboxylic acid. So there may be some synthesis where that's necessary to invoke as well. So here's an example. Take a look at this one, trying to analyze what reagents are necessary to do this synthesis. First thing I want to do is probably number the carbons. 1, 2, 3, 4, 5, 6, 7. Now on this side, I'm going to try to make these match up. So I'm actually going to count down. 7, 6, 5, 4, 3, 2, 1. So what's happening here? I've got 2 extra carbons. Call these 8 and 9. So somehow I have to add more carbons than 7 to get up to 9 total. Then I have to disconnect between 1 and 2. So this is adding carbons and then breaking them down. I do see these CO double bonds, and this is very similar to what we saw here. If I have an alkene and I use ozonolysis, I'll get 2 CO double bonds. So that's probably what I'm looking at in the last step. If I use ozonolysis in this last step, previous to reaction with ozonolysis, what this would have looked like would be this. Right, it would have had 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And the ozonolysis would have broken that double bond to produce these 2 CO double bonds. So now how do I get this structure into this one? So now I can see if I start with 7 carbons and I want 9, I've got to increase the length of the chain. And so the only way to do that is to use a base, NH2, to pick off this terminal proton. I shouldn't say the only way to do it, but the only way to do it with the reactions we've discussed is to make that into a nucleophile and then install the last 2 carbons by connecting them to a leaving group like a bromine or a chlorine. That should come in there and push that out. So now I have an alkene or an alkyne, and I need to convert that into an alkene. If I do the ozonolysis directly on the alkyne, just to point out, it'll still break, but it won't give me the correct functional groups. This one will be a carboxylic acid, and so would the other one. I'd still have the 9 carbons and they'd still be separated in the same spot, but I wouldn't have the aldehyde, I'd have the carboxylic acid. So that's why I have to convert the alkyne into the alkene first. And there are 2 ways to do that. If I want to make the trans alkene from the alkyne, I would start with sodium or lithium, and then and that would be an NH3, ammonia. If I wanted to make the alkyne into a cis alkene, I could use hydrogen and the Lindlar catalyst. Remember that one? The 2 hydrogens added at the same side, but once the alkyne is converted to the alkene, it stops reacting. In this case, it doesn't matter. I can use either one, because once I have the alkene, the ozonolysis is just going to break it anyway. So the stereochemistry, whether it's cis or trans, doesn't really matter ultimately. So that's a 1, 2, 3, 4 step synthesis. So you definitely want to practice those so that you can get good enough to work through them on an exam. So if there's a change in both the carbon skeleton and a change in the functional groups, it's going to be even more complicated, but you want to do the same thing. Look for how many carbons have been added or taken away, look at how the functional groups change, and then also focusing on regioselectivity and stereoselectivity to make sure that reactions connect things in the controlled way you're trying to get them to connect. But you've got to be familiar with a lot of reactions in order to get from point A to point B. So here's another example. Let's number these ones. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So here I have an extra carbon I have to add, and then I've got to get these two bromines connected in the right spatial arrangement. They both have solid wedges. So first thing I'd want to do, since this is already an alkyne, would be to remove this proton and replace it with carbon 8. So that would involve the similar reaction we saw last time. I would use NaNH2, and the NH2 minus is strong enough to pick off this proton. And then in step 2, I would add that methyl group. So I would use a methyl connected to like a leaving group, so that once this proton's picked up and the electrons stay behind, they can attack that methyl and push out the bromine. So after steps 1 and 2, the structure would look like this. It would have an extra methyl group there instead of a hydrogen. So that gives me the correct number of carbons. So how do I get these bromines on adjacent carbons? Well, we know there's one way to do that. If I start with an alkene at that position, I can add Br2 in the dark with carbon tetrachloride, and the two bromines will add across that pi bond. But that reaction that we know of, based on the mechanism, when we talked about that earlier today, we said the first bromine will form a 3-membered ring, and then the next bromine has to attack from behind to open up the 3-membered ring. And when it attacks from behind, it's going to end up in the opposite position from the other bromine. They're not going to have the same, they're not going to be on the same side. So what that means is, really, I've got to imagine rotating this bond. If I rotate that bond so that this carbonate flips over here, then this bromine will rotate under, and this will stay still because I've only rotated this part like a propeller. After we're done with lecture, you might want to make a model of this just to show yourself how it works. Much easier to see with a model. So now I can say, okay, if my carbon skeleton is spread out like this, and I have the trans pi bond or trans double bond here, then when I add the bromines, they'll add with the anti-addition across that pi bond, which is what these reaction conditions predict. So I have to have the trans alkene if I want to add the two bromines, one with the solid wedge and one with the dash wedge, so that when I rotate that bond into this rotational conformation, the two bromines will have the same, they'll both be pointing in the same spatial direction. So then how do I make the alkyne into an alkene and make it trans? I use sodium or lithium and ammonia. If you recall that reaction, the sodium donates an electron, it adds across the pi bond. Ooh, that looks familiar to what we've done this semester. So that makes a lone pair and a free radical. The lone pair picks up a proton from the ammonia. The free radical picks up another electron from the sodium to form a lone pair, and then that picks up another proton from ammonia, and those protons end up trans due to sterics. All right, so the last quiz question for today was a synthesis problem. So to analyze this one, you might also start by numbering the carbons. And this is a nice, simpler one than some of the ones we just did, but you definitely want to practice until you can get up to the point where you can do some of the more complicated ones. So what's happening here, though, is I need a bromine on carbon 5 and an OH on carbon 7. So some syntheses are easier to start from the beginning and work forward, sometimes from the end and work back, and then meet in the middle sometimes. In this case, since my reactant's an alkane, there's only one reaction that will work. And thankfully, there's one carbon that's tertiary, all the others are primary or quaternary, but there's no hydrogen there, so I can't react at that position. So if I use Br2 and light or heat, the bromine molecule will open to form radicals. The radical will abstract the hydrogen, that will produce a carbon radical. That carbon radical will pick up a bromine. So that should give me this structure. So even if you didn't remember anything from last semester, just from what we talked about this semester, there's only one reaction that will work on this alkene, and that's it, in a controlled way. So now I've got to get this OH group on there, and right now I've got hydrogens there. So there's no reaction we talked about where you can just get an OH to insert itself there or come in and push out a hydrogen. Hydrogen's not a good leaving group. I can't just replace it with an OH. So what I need to do is to do an elimination. So there's no hydrogen here. I don't have to worry about picking off a proton and forming a pi bond here. And since this methyl group and this methyl group are equivalent rotationally, it doesn't matter which of the 6 hydrogens is removed. I just need a base. Any strong base, ethoxide, terbutoxide, any of those strong bases will pick off any one of those 6 protons once it rotates antiperiplanar to the bromine. So I use a strong base to promote an E2 to push out the bromine as a leaving group. So it might seem weird that you're pushing out the bromine when you still want it there, but we don't really have any other options. So that'll make a pi bond. Now that I have a pi bond, I can think about adding a bromine and an OH across there. And I was expecting in a lot of your quiz answers for you to consider this option, the halohydrin reaction. And if you put that in your quiz answer, I'll probably give you credit for it. Well, I will give you credit for it, but it's not the best answer because in this halohydrin reaction, the Br2, this would also be done in the dark to avoid any radicals forming. But this pi bond would pick up the bromine would attack back, pushing out this bromine. So the first step here is the same as the Br2 reaction that forms the bromonium ion. But then by using water as the solvent, I expect water to attack. Now, just because I want the water to attack carbon-7 and end up then being deprotonated to leave behind an OH group at that position, that doesn't mean it's actually where it will attack. So just because you want something to happen, you got to understand the mechanism. And what we've been saying about these positively charged 3-membered rings is they start to open up from the side that can stabilize a positive better through hyperconjugation. And that will draw in the oxygen to that site. And so if that happens, that's the reaction you run, you'll end up with an OH connected here after the water attacks and is then deprotonated. And the bromine will end up here. You don't get the correct regiochemical outcome. So that's not the best way to do that. So let's look at an alternative. I didn't see any groups come up with this in your quiz answers. But, so we talked about how to get to here. So you'd still make the alkene the same way we talked about a minute ago. So instead of reacting Br2 and water to do the halohydrin reaction, another option, so just to remind you, we did Br2 and light or heat. And we used a base like ethoxide. So for the third step, if you use MCPBA, that will convert your alkene into an epoxide. Right? So the MCPBA is this per benzoic acid. It's got an extra oxygen that gets added across the pi bond into a three-membered ring or epoxide. So this gives me the oxygen I need. And so then the next step would be I've got to install a bromine here. I've got to open this up so that the oxygen will only be connected at this carbon. And I've got to add a hydrogen. So really I need a bromine and a hydrogen, HBr. So what that's going to do is the oxygen is going to pick up that proton. That's going to make a positive charge, and what we said is, in the very last reaction, when that positive charge forms in a three-membered ring, it will start to open up from the side that can stabilize a partial positive more, and that will attract this Br negative into that site, which will put it in the correct regiochemical position as the ring opens up, leaving an OH group at the other position. So HBr would be your fourth step there. So there may be other ways to do that, and I'll definitely look at your individual quiz answers and give you feedback on those to let you know if the route you've come up with is equally reasonable or if there are issues with it. So chapter 12 is probably not going to be your favorite chapter. Typically students don't enjoy the syntheses unless that you really remember the reactions from OChem 1 quite well, because there are so many of them. But it's important for us to go through this chapter and try to get good at some syntheses. At the very least, it will help you refresh your memory on a lot of the reactions from last semester, because a lot of them are similar to the reactions we're going to do this semester and can kind of act as a foundation on which you can build more reactions and knowledge to have success in this course. So here are the bullet points I'll use to give you an exam on day 3, which will be occurring next week. Right, so just to remind you, this week's exam, which is going to be happening tomorrow for the Tuesday students and Thursday for the Thursday students, it's going to be covering days 1 and 2. So next week's exam will cover days 3 and 4. So practice these problems from chapter 12, especially to help you practice some of these syntheses. And then we're going to finish up on Thursday, we're going to finish up chapter 12 and get into chapter 13. So I'd read those sections, maybe do a little preliminary practice for the examples embedded in those sections. And these videos can help you with a lot of those concepts and mechanisms as well. Any questions about anything from today? Any questions from anyone?
The lecture things will be posted where?
Yeah, so these videos I'm recording, great question, Cody. So if you go into Canvas, there's 2 ways to get to these videos. If you go into our Canvas course and scroll down to here, it'll be posted here. So these are the 2 from last week. You can also click on the YouTube playlist. And that will take you to the OChem 2 playlist. So what's nice about here, same videos, but what's nice about here is when you play them on YouTube, you can control the speed. So if there's a section I'm talking about that you feel confident with, you could increase how fast I'm going to get through that section faster, and then you can slow down on other sections if you need me to speak more slowly or whatever. So that's a minor advantage, but either location, whether it's the YouTube channel or the right there embedded within Canvas, you can get those videos. Good question. So Ku asks, which sections specifically from last semester are the syntheses things in? So if you're referring to the sections from last semester that include the reactions that you want to know in order to start solving syntheses, that would be everything from chapter 7, 8, 9, and 10. So there's really 4 chapters of reactions, starting from substitution, then through elimination, then addition, and then reactions with alkynes. So, I mean, you can go back to last semester's syllabus and look at what days that correlates to. I don't know offhand, unfortunately, whether that was day 12 through 18 or whatever, but it was definitely chapter 7, 8, 9, and 10. Any other questions?